is Earth, mass capital M, and radius, let's say it is R. Our satellite is orbiting Earth at a height is equal to R. This is orbiting Earth at a height equal to R from the surface of Earth. So obviously this has some energy also. What we wish is, we wish to lift this satellite of mass M to a greater height, let's say to a orbit which is at a height equal to 2R from the surface of Earth. When we have to lift it from here to here, then it is asked what is the energy which has to be supplied to the satellite so that this gets elevated or this moves from this orbit to this orbit. So once again what we do is we make use of the energy principle and work energy convertibility. When it is over here, let's say we take this as configuration 1, and when it is orbiting in this orbit, outer orbit of bigger radius, we call this as configuration 2. Now our intention is, what we'll do is we find the total mechanical system when this is orbiting in this orbit, and second is we'll find the total mechanical system when the satellite is orbiting in this orbit. And whatsoever the difference between these two mechanical energies, that much work it has to be supplied to this satellite to elevate it from this orbit to this orbit. So let's first talk about the configuration 1. We shall be talking about two things. One is potential energy, the second is kinetic energy. So over here it is minus gmm upon r. R from the center, r is the radius, r plus r, 2r. So this is potential energy, plus kinetic energy is half m v1 square, where v1 is the orbital velocity over here. We also know when this is moving in this circle, orbiting in this circle of radius 2r, so obviously that is, it requires a centripetal force mv square upon 2r. That is a requirement of the centripetal force. So this is the requirement, mv square upon r, where r is the 2r, r plus r, 2r, and this is going to be provided by force of attraction, that is force of gravitation, gm upon 2r square. So from here we can get the value of v1 square is equal to gm upon 2r. So we can put the value over here. So for configuration 1, total mechanical energy, it comes out to be minus gmm upon 2r plus half m v square is what? Gm upon 2r. And now when it is orbiting in a bigger orbit of radius r plus 2r, that is 3r, then the total mechanical energy of the system configuration is potential energy once again plus kinetic energy. So potential energy is going to be minus gmm upon r plus r, that is 2r plus r, 3r. So this is potential energy plus half m v2 square, where v2 is the orbital velocity when this is moving in an orbit of radius 3r. So this is second equation. We get this first equation, and now over here we have second equation. Now v2 is once again orbital velocity, and orbital velocity we can easily find once again using the concept of circular motion, that is mv square upon r. R is what, in which circle it is moving? R plus 2r, that is 3r. This is moving in a circle of 3r. So mv square upon r, that centripetal force, this is going to be provided by gmm upon 3r square. Gm upon r square. Centripetal force is being provided, the force of gravitation between Earth and this satellite. So once again from here we can get the value of v2. We can put it over here as we have done over here. We will get two equations, that is, one is total mechanical energy over here, 2 we have total mechanical energy over here, 1. So after that what we'll do is we'll find the total mechanical energy over here, we will find the total mechanical energy over here, and whatsoever is the difference between the two, that is total mechanical energy 2 minus total mechanical energy 1, this is equal to the work which needs to be done to move this satellite from this orbit to a higher orbit. This way we can find what is the work it has to be done, or what is the energy which has to be supplied for moving the satellite from a lower orbit to higher orbit. So once again what we have done is, first is we have found the total mechanical energy over here, Then we have found the total mechanical system when it is over here in the second configuration. And the total mechanical energy is potential energy plus kinetic energy. Potential energy is minus gmm upon r, where r is the distance between the centers of the two bodies. If we have to find the kinetic energy of this body, that is half mv square, v1 can be found using the concepts of circular motion, because this is orbiting in a circle, or we know what is the orbital velocity, where mv square upon r is going to be provided by the force of attraction, that is gravitational force of attraction, gm upon r square. Then we write one equation. Then similarly for the second one also, we find the potential energy, that is minus gm upon this distance plus half m v2 square, where v2 is the orbital velocity when it is moving in a circle of radius 3r. And from there we find the value of v2. After that we find what is the total mechanical energy, which is over here, what is over here. Whatsoever is the difference between these two total mechanical energies, that much work it has to be done to lift this body satellite from here to here, because work can be converted to energy, energy can be converted to work, work and energy both they have the same units as joule.